Hello! Today we'll be discussing Module 4, Sedimentation and Centrifugation Modeling. In order to determine how long we need to centrifuge or sediment a sample, we need to find out the speed at which the particles move towards the centrifuge wall, or the bottom of a settling tank, under various conditions, such as centrifugal speed. Let's begin with a force balance on a particle in a centrifuge. In a centrifugal field, we know the following relationship. V sub r equals omega r. V sub r is the velocity in the radial direction, omega is the angular velocity, and r is the radius. Now, the radius is the distance between the particle and the axis of rotation, so this is theoretically different from the radius of the centrifuge, but we'll talk a little bit more about that later. Let's also consider the relationship between centrifugal acceleration and angular velocity, which is g equals angular velocity squared times the radius, and g is centrifugal acceleration. So this is just a known equation. We can also say that g equals g prime little g, and that still equals the angular velocity squared times the radius. So now we have a lot of g's going on. So the first g is centrifugal acceleration. G prime is relative centrifugal force, also called RCF, or the dimensionless acceleration. So you have centrifugal acceleration, and then you have dimensionless acceleration. And then little g is just the force of gravity. So that's 9.8 meters divided by seconds squared. So when we think about this, the big thing is that RCF is really useful because it is translatable between different centrifuges. If you have a large centrifuge and a small centrifuge and spin them at the same number of revolutions per minute, the larger centrifuge is actually providing a lot more force than the small one because its radius is larger. So in order for a point on the outside of the centrifuge to make a full rotation, it must travel further than a point on the small centrifuge. Therefore, the angular velocity in the large centrifuge is faster. RCF is a measure of how many times gravity you would like to impart on your sample. Do you want to spin the sample at 150 G, for instance? In this case, 150 would be the RCF. Most centrifuges have a toggle button that will allow you to set the centrifuge up to run at a specific RPM or a specific RCF. If you read a protocol from an article and it mentions the RCF, you can replicate the protocol by setting your centrifuge to the same RCF. If the article mentioned RPM, you would need to know the specific type of centrifuge and rotor radius before you could calculate an RPM that would provide equivalent force in your centrifuge. Okay, so now let's go ahead and do a full force balance on the particle. So for this, we're going to say force equals mass times acceleration. So that's just kind of our basic physics equation there, which equals mass times dv sub r divided by t, so that's the velocity in the radial direction divided by time, equals f sub b plus f sub c plus f sub d. Now, these are our three forces that we can see in our diagram down here. And those forces are buoyancy, so that's trying to force the particle back towards the axis of rotation. Then we have F sub c, which is centrifugal force, and that's forcing the particle towards the wall. And then we have F sub d, which is the drag force, so the drag of the particle through the fluid, and that's going in the direction back towards the axis of rotation. Okay, so now we can outline each of those different forces in their own separate equations here. So the force of buoyancy equals negative being the direction of that force, indicating towards the axis of rotation. And that equals 4 divided by 3 pi rho naught, and rho naught in this case is the density of the fluid displaced by the particle. So again, buoyancy, times the radius of the particle cubed. So this is basically a way to calculate the size of a sphere. So we're assuming that our particle is a sphere, which is probably a pretty good assumption considering it's a cell. So we're calculating the volume of the particle and then multiplying it by the density of the fluid it's displacing. So we have a mass right here. This is mass. And then we have an acceleration term right here, which is our angular velocity squared times the radius of the centrifuge. Okay, F sub c is the centrifugal force, and for this we have a very similar equation to what we have up here, but in this case the mass needs to be of the particle. So simple rho is the density of the particle, and then we're also multiplying that by the angular velocity squared times the radius of the centrifuge. So again, we have our equation in mass times acceleration. In this case, this is positive because it's going towards the wall. The force for drag equals the surface area of the particle, so minus 6 pi, the radius of the particle, times the viscosity of the fluid, times the velocity of the particle under this increased force of gravity. So we call it big G. And this seems like a really long document, but I like to make sure that all of our variables are listed right next to the equation so that we're not confused. Okay, so very quickly the particle will reach its terminal velocity, aka it will be in steady state. We will assume this time to reach steady state is negligible. So now we will combine the last 4 equations along with this equation, which says dv sub r divided by dt equals 0. So that's the acceleration is 0. So now we can say m dv sub r divided by dt equals 0, as we showed in 4.8. And that equals our f sub b plus f sub c minus f sub d. If we rearrange that, we can get a velocity under centrifugal acceleration equals 2 divided by 9 times the viscosity, the radius of the particle squared, times the density of the particle minus the density of the fluid the particle is displacing, times the angular velocity squared times the radius of the centrifuge. Now, by remembering equation 4.3 above, we can utilize equation 4.10 in any of the following formats. So this is just to make things a little bit easier, whether the problem is defining the diameter of the particle versus the radius of the particle, whether you're given this big G term or an angular velocity term. So these are all the same. And I made them purple because purple is my favorite color, so good things show up purple. Okay, so now let's talk a little bit about settling tanks. So centrifuges basically do what a settling tank would do if given more time. So they just speed up the process because they're increasing that force of gravity. So settling tanks can be modeled very similarly to centrifuges because it's basically a centrifuge under the force of 1 times gravity, so under normal gravity. So here we say our centrifugal acceleration equals our RCF times gravity, and in this case our RCF is 1. So it's 1 times gravity. So we can modify our above equations to this equation here. So this is V sub little g, so the velocity under the force of normal gravity, equals 2 divided by 9 viscosity times the radius of the particle squared times the density of the particle minus the density of the fluid displaced times gravity. Now, this equation becomes a little more broadly useful later. So you might be able to utilize VG in your other equations using kind of this transformation that we see in 4.17, equation 417. So our velocity under centrifugal acceleration equals the velocity under gravity times that RCF term. So if we know our settling rate under normal gravity and we have our RCF, it basically just scales proportionally. So that's a very easy way to get the big G. In a sedimentation tank under normal gravity, the mean residence time of the liquid can be written as the volume of the tank divided by the volumetric flow rate. And that's the mean residence time. Now, why do we care about mean residence time? So if we consider the limiting particle, that's the particle that will take the longest to settle, it would be the particle that is at the very top of the tank. So we have to wait until that particle at the top goes all the way to the bottom. So similarly, when I mentioned that the radius in the centrifuge of a particle is basically the distance from the particle to the center of to the wall of the centrifuge. Well, that's not necessarily true because we're taking our limiting particle. So in that case, it would be whatever the furthest particle from the wall would be. Okay, so for a settling tank, we're just waiting for that particle at the top to go to the bottom of the tank. So we could say that if we want to make sure that our mean residence time is the same as the amount of time it takes for that limiting particle to settle, so all of our fluid has been clarified, we could say that the volume of the tank divided by the flow rate, volumetric flow rate, so this is our mean residence time, should equal the height of the tank, or length that particle must travel, divided by the velocity of the particle settling under gravity. If we rearrange that, we come up with our purple equation, meaning our good equation, and that will say that the volumetric flow rate equals Vg Vt divided by L. Now we can see that the volume of the tank divided by the height of the tank would be the cross-sectional area of the tank. So that's what we have over here. And then if we substitute in our early equation for the velocity under normal gravity, we end up with this equation here. So if we make our Q equal to this, then we would have a fully clarified solution. In the case of sedimentation tanks, A is the cross-sectional area of the tank, but more universally it could be considered the cross-sectional area of the fluid perpendicular to the direction of the velocity of the particle. So when a centrifuge spins, the fluid is pressed against the side of the centrifuge. So we will consider this in a moment here. Okay, so let's consider this term sigma. So we're going to talk a lot about sigma for the moment. Now sigma is the equivalent clarification area. So continuous centrifuges operate under the relationship that the volumetric flow rate should equal the velocity of the particle under normal gravity times the equivalent clarification area, sigma. Now, this is for all centrifuges, but the sigma will change depending on the geometry of the centrifuge. So sigma is the area that would be required if a gravity settling tank were being used instead of a centrifuge. So let's figure out what sigma is for a tubular centrifuge. Consider fluid velocity in the z direction down the axis in the centrifuge, shown here. So if we have the velocity down the axis of the centrifuge, so we're pumping stuff down the axis, that equals dz dt, equals the volumetric flow rate divided by the area of the fluid, so the cross-sectional area of the fluid in this case. So here, the cross-sectional area of the fluid would be pi times the radius from the axis all the way to the wall of the centrifuge, so the total radius of the centrifuge squared, minus the radius of the axis to the surface of the fluid. So in a tubular centrifuge or a tube bowl centrifuge, the fluid all gets pressed up against the side of the centrifuge, so it kind of has this big vortex in the middle. Okay, if we divide equation 422, so the last equation, on both sides by v sub big G, as shown in equation 417, we get Vz divided by Vg equals dz dr equals Qg divided by pi, the radius of the centrifuge squared minus the radius of the fluid squared, times the volume under gravity settling, times the angular velocity squared, times the radius of the centrifuge, or sorry, radius of the particle position in the centrifuge. For a limiting particle, this would be at R1, so at that surface of the fluid. Okay, so then we can integrate and rearrange and substitute equation 416 for v sub g. And this gives us an equation, one of our purple equations. So this is the volumetric flow rate equals our v sub little g equation. So that's this bracketed term right here, times this, which is our sigma. So this term right here is actually our sigma for a tube bowl centrifuge. Now, this equation Q equals V sub G sigma is utilized for all centrifuges, but for some of them, like a disc stack centrifuge, the geometry of that's more complicated. So we're not going to derive all of these equations here, but I will say that I've listed them here if you would like to take a look at what some of the other equations are. One note is that we generally make this substitution, which makes our equation 426 much more simple. And that is that r naught squared minus r1 squared divided by the ln of r naught divided by r1 equals 2r squared, where r is simply the radius of the centrifuge. This has a little bit of some complicated math attached to it, so if you're interested in why this is the case and why that's true, you could visit the document for y 2r squared that is listed on the Canvas page. Okay, a few notes. So generally, process parameters are determined by clarifying a sample in a laboratory centrifuge. You can calculate the settling velocity by running the sample and checking it at various times until the supernatant is clear. So you can just pull it out and you can see whether it's clear or whether it still is kind of cloudy. The height of the fluid in your centrifuge tube divided by the time you ran it is your settling velocity under the centrifugal acceleration. So that's your settling velocity in your centrifuge. Then you can use equation 417 to find the settling velocity under normal gravity, because you know what the RCF of your centrifuge was. From there, you can use equation 421 and the appropriate sigma. So those are those flow rate equations with the sigma to find the flow rate for your broth through the industrial centrifuge. You can maintain your RCF between the lab scale and the grand scale industrial machines. So that's generally how you would go about finding the process parameters for your industrial centrifuges. Here are some other useful notes on heuristics. You'll also see them in Dr. Kelly's notes packet. So efficiency of separation is proportional to the square of the diameter of the particle to be removed. The density difference between the particle being removed and the surrounding liquid is very important. If you have something that is closer in density, it will be a lot harder to separate out. So maybe you should consider something like a filtration in that case. Increases in viscosity decrease separation efficiency. So often like a 25 to 50% dilution of feed can really help your efficiency. Sedimentation rates are thousands of times greater than the pull of gravity. Mammalian cell broths typically have 2 to 6% cell volume per volume, while yeast cell broths have up to 30%. So the viscosity of the mammalian cell broths we would expect to be about the same as water, whereas yeast, you have a lot more volume being taken up by the actual solids. So bacterial cultivations, probably something like 15 to 20% volume is the bacteria. Mammalian cell density and yeast cell density are shown here. So these are kind of what you're going to base your calculations off of when we're looking at the densities. Disc stack solid cake can be as low as 50% moisture. So it's pretty good at dewatering. Okay, so this table kind of shows how you would choose which type of centrifuge you want to use. So if you have a lot of solids, meaning you have like a yeast broth or a bacterial broth, and you don't want to add a bunch of water to that, then basically you would want to choose a decanter. So one of those scrolling centrifuges that dump out all of your solids on the other end. If you have, and this could be sort of a lot of solids, 20% is kind of a lot of solids, would be for a disc stack. If you have less than 1% or less than 5%, you'd be looking at a tube or a chamber bowl. All right, so that'll conclude our lectures on sedimentation and centrifugation. Thank you.